Hello everyone and welcome. My name is Dr. Sayantika Chowdhury. Today, we're going to build a bridge, but no, not with bricks and mortar. We're building a digital bridge, the one that connects our physical world to the world of computers. We're talking about analog to digital and digital to analog converters.
Have you ever just stopped and wondered, how does the sound of your voice, or a guitar, get from the real world into your phone as a digital file? Or how does your air conditioner know the exact temperature of the room? These are all real-world analog things, but our devices, they only speak digital. So how do they talk to each other? Well, that's the exact puzzle we're going to solve today.
To really get this digital bridge, we first need to properly understand the two worlds it connects. You can think of them like two different countries that speak completely different languages.
On one side, you have the analog world. This is the world we live in, a world of smooth, continuous change, like a gentle ramp. The temperature doesn't just jump from 25 degrees to 26, it flows through every possible value in between. But on the other side, you have the digital world of our computers. And this world is all about precise, discrete steps, kind of like a staircase. It only understands two things, high or low, which we represent as ones and zeros.
Okay, so this diagram shows the whole journey. First, something like a microphone or a thermometer, what we engineers call a transducer. It captures a real-world signal, like sound or heat, and turns it into an electrical analog signal. Then, the ADC, our first bridge, converts that smooth signal into a series of ones and zeros for the computer. After the computer does all its processing, it sends a new digital signal to the DAC, our second bridge, which turns it back into an analog signal to do something in the real world, like playing music through your speaker. So let's start with that first bridge, the one that takes the computer's language and translates it back into our world. This is the digital to analog converter, or, as we all call it, the DAC.
So what is a DAC really? Well, you can think of it as a translator. It takes a digital number, a string of ones and zeros, and it converts it into a very specific proportional analog voltage. The bigger the digital number, the higher the voltage. It's as simple as that.
Now, my favorite way to understand this is what I call the chef's recipe analogy. It's fun. Imagine the binary number, let's say 1010, is our recipe card. Each bit is an ingredient with a specific weight. The most significant bit, or MSB, is like the main ingredient, a full cup of flour. But the least significant bit, the LSB, is just a tiny pinch of salt. An op-amp circuit then acts like our master chef, summing up all these weighted ingredients to create the final dish, which is our analog voltage.
And here it is. This is the actual circuit that brings our recipe to life. You see those different resistors? They are what give each ingredient its proper weight. The most important bit gets the smallest resistor, letting the most current flow. That's our cup of flour. The least important bit gets the largest resistor, letting only a tiny bit of current through, our pinch of salt. And the op-amp, that's our chef, acting as a summing amplifier, mixing everything together perfectly.
Now, this recipe is fantastic in theory, but it has a really big practical problem. Imagine you need a high-quality 12-bit DAC. You would need a huge range of very, very precise resistor values, and manufacturing that is a nightmare. So let me ask you, what is the main drawback of using such a wide range of resistor values for this recipe?
That's the exact problem engineers were facing, and they came up with a truly brilliant solution. So let's see how they built a better, much more practical bridge.
And the solution is called the R/2R DAC. Now look at this. Instead of needing a whole bunch of different resistors, this design cleverly uses only two values, R and 2R. This makes it so much easier to manufacture accurately, especially when you're making high-resolution converters. It's a simple, elegant, and really powerful solution.
This circuit is just a beautiful example of smart engineering. You see, the repetitive ladder structure, it gives us the same binary weighting we need, but with just two resistor values. It's a practical, scalable design that really makes high-resolution DACs possible in the real world. Okay, so we've built a solid bridge from the digital world back to ours. But what about going the other way? How do we take a real-world signal and turn it into those ones and zeros? Well, for that, we need our second bridge, the analog to digital converter, or ADC.
Now, here's the thing. You can't just convert a continuous signal all at once because it's always changing. So what do? We have to take snapshots of it, like taking a series of photos. This process is called sampling. And to get a really clean, stable snapshot, we use a special sample and hold circuit. It samples the voltage in a flash and then holds it steady, freezing it in time so the ADC has a stable value to measure. This is absolutely crucial for an accurate conversion.
One of the simplest ways to build an ADC is with what's called a digital ramp ADC. And to understand how it works, I want you to imagine we're playing a little game. A game of guessing someone's height, but all we have is a staircase. This circuit does something very, very similar.
Okay, so let's play the guess the height game. The analog voltage we want to measure, that is the person's unknown height. A digital counter starts counting up from 0. With each count, the DAC we just learned about creates a voltage that goes up one step at a time, just like a staircase. A special circuit called a comparator is constantly asking, is our staircase voltage higher than the person's height yet? And the very instant it is, the comparator shouts, stop, to the counter. The final number that the counter stopped on, that is our digital value for the height.
Now, this method works, but there's a catch. Just like it would take longer to climb the stairs to measure a very tall person, the time it takes for this ADC to guess the analog value depends on something. So, what do you think that is?
Building a bridge is one thing, but its quality really matters. Is it a rickety old rope bridge, or is it a super smooth expressway? With converters, there are a few key specifications that tell us exactly how good our bridge really is.
The most important spec, by far, is resolution. And all it is, really, is the size of the steps in our staircase. The smaller the steps, the more precise the measurement can be, and the higher the resolution. A high-resolution converter can detect even tiny changes in a signal.
This table shows you exactly why the number of bits matters so much. An 8-bit converter, that gives you 255 steps. It's a bit bumpy. But a 12-bit converter, whoa, that gives you over 4,000 steps. With that many tiny steps, our staircase becomes so smooth, it's almost like a perfect ramp, giving us a much more accurate picture of the original signal. Now, because we're using steps to approximate a smooth ramp, there's always going to be a tiny bit of error between the real analog value and its digital version. So, what is the term for this built-in error that's caused by the step-like nature of the converter?
All right, we've covered a lot today, from our chef's recipe DAC to the Guess the Height ADC. So let's recap and see why understanding this digital bridge is so incredibly important for any electronics engineer.
So, what are the key takeaways? It's simple. The real world is analog. Our devices are digital. DACs are the translators from digital to analog. Remember the chef's recipe? ADCs are the translators from analog to digital. Remember the guess the height game. And most importantly, the resolution, which is just the number of bits, determines the quality, the smoothness of our bridge. These converters are the unsung heroes inside almost every single piece of technology you use.
And I want to leave you with this. Understanding these concepts isn't just about passing your exams. It's about unlocking your potential to create. When you truly understand how the analog and digital worlds talk to each other, you can build the sensors for smarter AI, you can design life-saving medical devices, or you could create the next big thing in digital music. This knowledge, this is your key to becoming an architect of the future.